The screen is visible.
Yes, sir. The screen is visible.
So I hope we can start now. Uh, Everyone is available in the meeting. So today I welcome you all for the session of a short course on the basics of computational fluid dynamics with ANSYS Fluent. So instead of today directly going into the ANSYS Fluent introduction, I just want to give this today's session as what is a computational fluid dynamics and myself, Gangadhar Venkatramana. I'm a Prime Minister Research Fellow in the Department of Aerospace Engineering, IIT Kharagpur. And thanks for giving this opportunity for the college administration and management and all the faculties. And my special thanks to Arhit also so for arranging all these things. And without any delay, I just also want to introduce myself and about my professor also, what we are actually doing in IIT Kharagpur as a PhD scholar, and my professor area, what he actually worked in his PhD, and what we are right now interested on. So myself, as I discussed, my name is Gangadhar. Like I did my bachelor's, then I joined as a PhD, both in aerospace engineering. Then as a PhD part, my work is completely to understand the physics involved with the flow over flapping fins. I can say clearly that terminology is flippers. Like if you say wings of a whale, whales are very big structures, very big animals. I can say mammals in the sea, underwater sea. So those mammals has a fins or a wings like a wings kind of structure, like a birds. How do they have wings? So these mammals also has wings. So those wings has some kind of special attention drawn by because of its unique characteristics that we are trying to investigate. What are those? What why we are having? Why we are looking at those unique characteristics? What are the special abilities of those wings, especially for the whales? Not looking in the birds case, we are looking at the whales case. So that is actually my part. I do it in both simulation wise and also experimental wise. So coming to my professor name is Professor Sunil Manohar Das. He did his doctorate from National University of Singapore, and then he's also completely right now as a assistant professor from IIT Kharagpur, aerospace engineering, and his area is also like understanding of aerodynamics related to and stability issues related to MAVs and underwater vehicles, and also he's an expert in develop of solvers, fluid flow solvers. I can say simulation, how to develop the code for simulating the fluid flow for any real-time cases. So he is specifically very interested in that area called lattice Boltzmann method. So that is a short introduction about myself and my professor. So let's dive into the topic today. So I hope everything is clear. My because I don't see any feedback from your side. So in the intermittently, I would like to ask like whether whether you are able to see my slides or not, whether my communication or everything is proper or not. I don't want to get the interruption with the internet. Arhit, is it everything fine?
Yes, sir. It is
It's
fine, sir.
streamlined. Okay, fine.
Yes, sir.
So
Yes, sir.
intermediately, I would like to ask that so that I can ensure that it is not disconnected. Okay. So now we will just have a brief idea today what is actually this computational fluid dynamics. So the short term for this is that we always use every time in our real life is CFD. The CFD we say it as a computational fluid dynamics, but the actual the more sarcastic way people used to call it as a computer-aided fluid dynamics. Sorry, not sarcastic way. Its actual name is a computer-aided fluid dynamics or computational fluid dynamics. Or also one more way that uh, the CFD is treated in real life sense is colorful fluid dynamics. That I will just let you know what are all the details of what is the CFD, how the letters each C, A, F, D is uh, defined in real physics and other other aspects. So you see the CFD here that I'm showing one picture. Here it is showing some aeroplane. Let me take some laser pointer options and then this. So here you are seeing some aeroplane and some lines over the aeroplane and some beautiful colors over the aeroplane and what else? Many things are we are seeing here, and We need to understand few things from these colors. What is this color? Why we are studying aeroplane? What actually the reason we are studying the aeroplane? What is the importance of studying the aeroplane in simulation way? That means why not in an experimental way? What is why we are doing like this? So let me show you the complete slide, then we can discuss it better way. So not only the aeroplane, why we are doing the simulation is the first question that everyone needs to understand. We are testing some objects. The first best example for learning about the CFD is understanding the physics, how aeroplane is flying. I just want to simply know that how many of you know how aeroplane is flying? If you know, just can you raise the hand through the Teams? Is there any option for you available there? Yes, Parvar. Other? Can you hear me? Like, is my question is clear? How many of you know about the aeroplane is flying? I don't ask you, but if you know the some physics, at least some physics that you understood about aeroplane, that will be so helpful for proceeding further. If not, I will inform you that. Anyone knows about how this aeroplane is flying? Arhit?
Yes, sir. Am I audible, sir?
Yes.
Yes, sir.
You know, right?
Yes,
Can
sir.
you
Yes,
raise your
sir.
hand? If no, you are knowing, can you raise your hand in this Teams?
Yes, sir. I think, sir, I can. Yes, sir.
Yes, like that. So, how many of you don't know that how aeroplane is flying? Raise your hand. How many of you don't know that aeroplane, how aeroplane is flying? So please raise your hand. Okay, Ajoy, you guess. Ranjal Bhattacharya. Okay. So most of you don't know how aeroplane is flying. That is fine. So now, I give me a second. I'm joining with other. Fine. So now I see most of you raise your hand. That Sayak Sardar, Ajoy, Pranjal, and okay, fine. So you don't know how the aeroplane is flying. That is fine, but not an issue. The use of CFD may better explain few things, that vehicles or animals that use fluid as a medium that can fly high or that can propel or for any other purpose. Let me say the clear example. Um, Best examples are the birds. They are using the fluid energy by some means. By some means, they are using the fluid energy and they are flying. And the same way, the vehicles, if I say aeroplane or any other vehicles, I can say UAV drones or micro aerial vehicles. So all the vehicles that are flying in air, they are also using some principle to fly in the air. Not only in the air, in the water also, the swimming. The swimming also like use of fluid energy to swim inside or to float inside or to travel with a high speed. So these are all the things involves with some physics. They are mainly focusing on to use this fluid energy for the required propulsion. I can say one thing, aeroplane is flying, but it is not propelling by the fluid. If you are getting my question, I will, I don't know. Let me clear the question. Aeroplane is flying with the fluid energy. This aeroplane is flying with the fluid energy, using the fluid energy, but the propulsion is coming from this jet engines. How many of you know this? What about this? Or what are these jet engines? Jet engines, Sayak, Sardar, you know what is a jet engine? Okay, Parvar, you know, right? How many of you don't know what is a jet engine? How many of you don't know what is a jet engine? Okay, okay. So jet engine is similar to like your IC engine, where your IC engine directly gives you the mechanical energy that you couple with your wheel directly to the vehicle wheel, and wheel rotates that you for you getting the any transmission, not only for vehicles, not only for the automobiles, for any other machinery, that you are getting your mechanical energy directly through the rotation of your IC engine. Like I'll say, by the end of the power generation, you will get a flywheel. From that flywheel also, or from the crankshaft also, you are getting your connection, and you are connecting that directly to your machinery. That is how IC engine works. Here also, the jet engine is producing some power, but it does not directly connect it to any of the component. It just propels some liquid. It just propels some fluid, uh, like a rocket. So everyone right how rocket works. It propels some liquid or some burning gases through its exit. I hope you all seen the recent recent launches of ISRO. So in the same way, the jet engine also propels some, pushes out most of the burning gases, all everything, the flames. It pushes out of the jet engine. With that energy, like as I say, for every action there is an equal and opposite reaction. Like how the rocket flies, because of its pushing the fluid out of its rocket, it is getting a force, reaction force, and it is lifting up. In the same way, these jet engines are also creating the thrust. It pushes, or I can say, it throws the most amount of burning gases. There are gases, or I can say fuel, aviation fuel that burns inside with a lot mixture of air, and mixture of this air and fuel will pushes the fluid outside. So it is only giving you thrust. Thrust in the sense the same way how rocket is propelling. Here also you can see the propulsion of the jet, because it is pushing some fluid outside with high velocity, and with the reaction you are getting some thrust on the jet engine. So with that thrust, the aeroplane is moving forward. Okay, now engine part is over, everything is over. The aeroplane is moving forward with some high velocity. Suppose I say 100 to 500 to 800 kilometers per hour. With that velocity, suppose the aeroplane is moving forward. I'm still saying it is on the ground. So now I'm not going into the air. I'm still saying it is still taking. It is now on the runway and ready to take off. So during the takeoff, it needs to travel for a very long distance on the runway. So only after traveling a long distance on the runway, any aeroplane can lift off to the air. Why it cannot lift off like a bird? Suddenly it cannot lift off like a bird. What is the physics involved in that? So to understand that, what we need to do, you need to design an aeroplane in a model, like a CAD model, any CAD model that SolidWorks or AutoCAD, whatever it is, so CATIA. So model an aeroplane in that, and instead of and ask you after modeling that, bring that CAD model into the ANSYS Fluent or any commercial software. Once you imported that model into your commercial software, you now allow the aeroplane to move at that high speed. Like what is it moving that high speed? Instead of moving your aeroplane with the high speed forward, like if it is this is my aeroplane, if instead of moving my aeroplane with the high speed, like around that 800 or 1000 kilometers per hour, now I will allow my fluid. I will fix my aeroplane like this, and I will allow my fluid at high speed, the same speed what actually aeroplane is traveling. Is the both are similar? Sorry, are these both are similar? How many of you understand this concept? Can you please raise your hand? What I'm saying is, instead of allowing my aeroplane to move forward, I'm now trying to understand why aeroplane is trying to take why aeroplane how aeroplane is taking getting the lift to move upward like this. Aeroplane is moving upward like this after only traveling with that high speed on the runway for a long distance. So you all got the idea. What is it? So now to understand how it is lifting up, I want to do the simulation. To do the simulation, what I need to do is I need to first design that CAD model in any software, whatever you want, and you can import into the ANSYS Fluent software. So now you imported it. After importing, what you need to do, you need to fix your geometry first, and instead of allowing your geometry to move at that velocity, you can allow your fluid. Both are relative, right? Either you move your object at that high speed, or you allow the flow. Flow means the incoming air flow. Because of it is movement, that you will see the relative air also coming on the same speed. So I will allow my flow to move on this aeroplane with some high speed. So what is happened? I am now simulating the real life situation in the use with the use of software. So what are the outputs I will get? I can see what are the forces acting on this aeroplane because of this very high speed of the fluid, right? Did you get it? Hope you all get
Yes, sir.
this
Yes, sir. Yes.
concept. Yeah, nice. Yeah, you can just please raise your hand. I can see whether you're following or not, so I can also understand. So this is why I'm simulating the fluid flow over an object. I want to see what are the forces acting on the this particular aeroplane. Okay, you can down your hands. So what are the forces acting on this aeroplane? I am simulating that. And also, what else I can see? What else I can see? Not only the amount of force. If I say by doing the simulation, I'm getting that there is some amount of force acting in the upward direction that is actually lifting the aeroplane upward. By moving that at high speed, some forces are acting on the aeroplane because of this movement of flow. So that using that force, my aeroplane is moving upward. Okay, that is fine. But what are the sources of the forces? The sources are purely because of flow over air of the flow over this high speed flow over the aeroplane or any other things. Any other things are also involved in that. So to better understand that, we need to analyze the complete structure over the aeroplane, like the way we are seeing here in this here. I hope you are all seeing this picture. So I need to understand the complete structure of the fluid all over the aeroplane, right? Why I need to understand? Why I need to understand means you are getting some force, but what are the root causes of the force? What is the speed and the aeroplane should travel at what velocity of the aeroplane that it gets sufficient force so that it can overcome its self weight and can lift off into the air. Got it? So many things that we need to understand before uh, designing an aeroplane. So now, suppose I will take Arhit. Arhit design some aeroplane model like this, and he is now interested to learn uh, at what velocity my aeroplane will lift off. So from his design, we will assume like a small micro aero vehicle. So from his design, it is aeroplane small model. I'm not saying a big model. So this small model he designed with around say 10 kg of total weight and additional, including all the fuel or battery supply source. So now he needs to understand at what velocity his aeroplane should travel first on the runway before it gets a sufficient force to lift off. We are clear that the aeroplane should travel with a high speed on the runway, then only it gets a sufficient force. I'm just saying that, but how we are getting that forces that you need to understand clearly from the flow structure on the aeroplane. But his task is to what velocity the aeroplane needs to achieve so that it can lift off high. Okay. So now he understood that some particular velocity that aeroplane should travel, then only my aeroplane will lift off. That is very good. So what he needs to do if he wants to decrease the velocity, but still he at low velocity itself. Suppose he is getting 20 meters per second. If his aeroplane is traveling at 20 meters per second, and he is able to get a lift on the aeroplane, but his target is to he can only move his aeroplane at 10 meters per second, not much more than that. So what he needs to do? What physics we need to make it here? To achieve that at low velocity itself, his aeroplane should get lifted. So all these questions, you see now itself, we are getting so many questions, right? So all these questions can be clearly understood only after understanding how fluid is moving on top of the aeroplane. What are the key sources of generating the lift? Okay, so you see these wings. Without these wings, you won't get any lift on the aeroplane. So how these wings are playing a key role on generation of the lift. Lift means the upward force. Lift means the upward force that is taking the aeroplane up into the air. So what are the forces that are generating on the wing? You need to understand by looking at the structure. So I will just give you a brief idea. Suppose this is a which kind of contour I can say this is a velocity contour. Velocity contour means flow velocity contour. Let me write it here. So these are velocity contours. Okay. So velocity contours means the color indication you need is telling us what is the velocity at every level. Suppose extremely blue. Blue region is low velocity, and red region high velocity. Are you getting my point? That means your aeroplane is traveling at a speed of, suppose, 1000 kmph. My aeroplane is traveling at a speed of 1000 kmph. But at every location on the aeroplane, if I take a point here, 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 or here, here, anywhere, my fluid velocity, or if you are standing there, you will see more velocity than the 1000, more or less velocity than the 1000 kilometers per hour. I hope you are all getting this point. If you understood this content, then just please raise your hand. Okay, thank you. You can down your hands now. So why I am seeing more velocity? Why I'm seeing more velocity is because you are placing some object in the fluid. The fluid is here, and you are moving with a high velocity around 1000 kilometers per hour. And if you are standing on top of the aeroplane and you are measuring the velocity here, you will see more velocity, more than 1000 kilometers per hour. And if you are standing here, you will see very less velocity of the fluid, that is less than 1000 kilometers per hour. If you are standing here at this point, you will see, if you're standing at this point, you will see again more velocity, more than 1000 kilometers per hour. Suppose this orange, I can say reference velocity as 1000 kilometers per hour. If you go to this region, that means exactly the top of the aeroplane, you will see more than 1000 kilometers per hour velocity. If you go to this region, that means going means not physically going. You're just going and sensing, you're measuring with the sensor, some sensor that you're using. If you're sensing, if you're measuring the velocity at this particular region, at the nose of the aeroplane, you will see less velocity. Again, at the top of the wings, if you measure, you will see again high velocity. So why this velocity is changing on top of the aeroplane? So what is the relation between this velocity and the forces? Okay, so there is a relation between this velocity, pressure. How many of you know what is a relation? Basic relation. I don't want to go into the advanced relations. Basic relation of velocity and pressure. How many of you know what is? I mean, just heard about whether you heard the Bernoulli's relation or not. I'm not going to the governing equation. I'm just asking from your fundamental fluids that what is a, like, have you at least heard what is a Bernoulli's equation? Six numbers: Sayak, Aman, Ajoy, Parvar, Arhit, Mohit, Priyansh. Fine. So if you already heard about what is a Bernoulli's equation, then it is fine. If you are not aware of it, you can just refer to what is a Bernoulli's equation. So Bernoulli's equation can relate your pressure to your velocity. So if you have a velocity at this particular location, you can find out the velocity at the sorry, you can, if you have the velocity at the particular location, you can find out the corresponding pressure also. Okay. So I'm getting now pressure. Pressure is the key thing that generate the forces on your object, right? Suppose you all well known about the submarine. Many recent submarine incidents are also happened that there is a blast of a submarine that team went for seeing the Titanic. So that I forgot the name, Ocean Gate, I think. The name is Ocean Gate. So Ocean Gate went tried to see the Titanic in the deep sea, but unfortunately, because of the overpressure or overload on the Ocean Gate submarine, it got blasted. That means if you are going in deep of the fluids, your pressure on the top of the surface is going to change. The pressure distribution is a key factor that says how much of the forces are, how much the amount of forces acting on your object. In the same way, aeroplane is traveling in the air and some high velocity, and the velocity is changing the corresponding. So if there is a high velocity here, it is changing the pressure of this location, and if it is a similar way in other locations, it is changing the pressure also. So if it is changing the pressure, that means the corresponding local force, if there is a difference in pressure, you will definitely experience some force at that particular location. Okay, so at that particular location, you are seeing some force. So those forces will combinedly. So there are many forces acting on, not many forces, at every point you will see some force. So those, all the forces are combinedly giving a single resultant force. If you integrate the pressure over complete surface of this aeroplane, then you will get a resultant force. Okay. So now how I can get this kind of contours? Yes, sir. If you have any question?
Sir, actually, I have one question regarding these
Yes.
velocity contours. Like we can see that there are different colors to determine the velocity contour or velocity. Like, is it, sir, the velocity intensity at a particular point,
It's
or
a velocity
will it also?
magnitude.
Okay, sir, magnitude of the velocity. So, sir, how
Magnitude of
can we determine the direction of the velocity? Like, since velocity is a vector, so, sir, can we also determine the vector means direction of the velocity using the CFD?
Yes, good question. So we can also determine the direction of the velocity by using the vectors plotting. We can plot the vectors direction of the velocity parameter. So that we will also see in the upcoming classes how to plot, like, so you now you can see the direction of the vectors. There is a simulation of fluid flow over the curve. Are you able to see here? So this simulation is
Yes,
showing
sir.
the velocity vectors also. So that is saying that what is the direction of the velocity at that particular location. And the length of the vector says what is the magnitude of your velocity. Okay. So now that's a good question. You can down your hand. So velocity vectors also you can generate from the CFD, and you can understand how the fluid is moving at that particular location, what direction the fluid is moving at that particular location. So once you get your velocity contours and also the pressure contours like this, you can investigate at what location there is a high pressure, at what are the locations there are low pressure. With that information, you can understand how this lift is generating, how the forces are generating. So I hope now you're all clear why we are doing the CFD on any object. The main purpose is not only about the forces generation, but for your understanding and for your interest on the for your, maybe you can better know about an aeroplane. So I thought I took aeroplane. It's not only about the aeroplane. There are many other applications of the CFD. So you will get the simple idea of, not only simple idea, if you do the realistic things like measuring every parameter exactly from the real life model, and you are scaling to the simulation and in the computer, and you are doing the correct simulation, you will get the very accurate results of how much of force acting on my aeroplane if my aeroplane is moving at the 1,000 kilometers per hour or whatever the velocity that you are moving. Okay, if that much of force is acting on the object, what are the responsible things? To understand what are the responsible things, first I need to generate the contours like this. These are the contours. The contours also saying that where is the high velocity or where is the low pressure. These kind of information you will get. If there is somewhere here there is a low pressure and somewhere here there is a high pressure, you will see that because of the difference of a low pressure here and high pressure here, you will see a force in this downward direction. That means here is a low pressure and here is a high pressure. If I am saying, first suppose this is a low and high pressure, you will see a net downward force. So something, a net downward force that aeroplane will experience. So these kind of investigation you can do on any object for better, some more understanding that people mostly they perform on this fluid analysis on F1 car racing also. So the F1 cars also moves at very high speed, such that without a proper design, um, the car cannot allow to go to that high speeds, because if you're moving at high speed, as the same way that aeroplane is lifting off from the ground, your car may also lift off from the ground and it can fly. I hope how many of you seen that flying cars in F1 race? The cars are flying because of whatever is the reason, but how many of you seen that cars also flies in F1 car race? Okay, Aman and Sardar. Okay, Sarkar, good. So the reason is also hidden in that, because you will see if your improper aerodynamic design is incorporated in your F1 car racing, instead of going on the land, it can fly in the air for some time and it will again fall down, but it will fly in the air, it will lift off from the ground, it will lose the friction. My professor told that a car is meant for traveling on the road. It's not meant for flying in the air. right? So for that purpose, why we need to, so for that purpose, what we need to do, we should design a car also which is going at a high speed in such a way that it should not lift off from the ground. It should get a sufficient friction between its tires and the road, right? So the best example of F1 car racing, where before designing any car that is going at high speed, you should also think about the aerodynamics, whether it is creating a sufficient friction or not. Okay, hope up to this everyone is clear about what is the idea that we are looking for, why we are simulating the fluid. Simulating the fluid, I'm saying the simulating the fluid on the objects using the CF, using the software, any commercial software. So I hope you all clear why we are doing this. What is the use of or what is the necessity of the CFD in your daily life or your real life applications? Everyone clear or any doubts so far? You can raise your hand if you have any doubts, or if you have any doubts, can you please raise your hand? I will just clarify because before moving to the next slide. Yes, sir.
Sir, I have a general doubt. As you have told that we keep the object fixed and we try to simulate the flow.
Yes.
So why? What is the main reason that we do it? Like we can also reverse it for actual cases. Like if we are keeping the fluid stable and we are like taking the object into motion. So why not we do the reverse thing? Like what is the basic reason behind it?
The basic reason that you want to move your object at some speed,
Yes,
right?
sir. Yes, sir.
So
I
I will
want
tell
to.
you,
Yes, sir.
hmm, I will
I
tell
want to
you
keep the
the,
fluid static and I want to keep like the object we moving. So why can't we do that in
okay,
simulations?
I will ask you in another way. Suppose you are watching a movie. In that movie, you are seeing some aeroplane is traveling. Okay, what do you see? That you are seeing an aeroplane. I mean, the cameraman, whatever he is trying to capture, he captures only the aeroplane. So that means his movement of the camera also moves with the aeroplane location, isn't it?
Yes, sir.
So in that picture, if you are seeing that the aeroplane is moving, whether are you really seeing that aeroplane is moving or the fluid is moving?
So we can see that the aeroplane is moving. Like if we set the frame
That
of reference, fluid will be
that's
moving,
a
sir. Fluid will be
this
moving.
you have to set the frame of reference. So
Yes,
in
sir.
your frame of reference, to make the audience feel that the aeroplane is flying, he only captures to the aeroplane and he moves his camera in such a way that that aeroplane is also moving and gives some animation that the fluid is coming on top of the aeroplane, right?
Yes, sir.
Here, our primary objective is to best example. Suppose this is my jet aircraft. So if I want to conduct some study, I can create some domain like my framework. I can create some particular domain and I can allow my fluid to flow in this domain. So I can study the fluid flow on the top of this aeroplane, right? If you are doing the same thing in a reverse way, that filling this entire domain means the amount of area that you are capturing in your simulation. That means you are not able to capture the whole sky or the whole earth in your simulation, right? For real life fluid. You can only capture a small amount of area of air or small amount of space in your simulation. So I'm capturing a small amount of space and now I am allowing in my aircraft to travel. Suppose it is a position A, this is my aircraft and it is traveling like this forward. So what is the amount of space it can travel? If this is my area captured that I do the simulation, I captured suppose this is a 1 kilometer space. Okay. This is my 1 kilometer space I designed and I'm trying to capture the movement of aeroplane in this space. If you are doing that, you can move your aeroplane from here to this part, from point A to B, right? So you can only do the simulation from point A to point B and you can see the flow over the physics. But after coming to the point B, your aeroplane is going out of your focus area. I can say in the camera way, there is a camera seeing this particular area, the red box area. Okay. So this box is seeing some particular area. In the same way, in the simulations also, you need to capture some particular area to do the simulation. So how the camera is seeing? Camera is seeing this particular area. And now in the camera, I'm seeing that an aeroplane is moving from point A to point B. Got it? If the aeroplane is out of this frame, that you won't see any object in the field. This is the field I captured. So you, if the aeroplane is out of this field, I won't see any object in the field. But that is not my requirement. My requirement is only to see the flow on the aeroplane, right? Or to see the flow on the aircraft. I'm not interested to see the flow only inside this domain. Are you able to understand, Arhit?
Yes, sir. Yes, sir.
So my requirement is only to see the flow over the aeroplane. I only see my aeroplane and I move with my aeroplane, right?
Yes, sir.
If you are moving with the aeroplane, that means I'm focusing only on the aeroplane and I'm measuring how the velocity is changing. So why can't I do in the reverse way? So that's way, that means I fix my aeroplane also like this, and I will allow the fluid to move on the top of the aeroplane instead of my aeroplane moving or my aircraft moving in the domain. Isn't that a good idea that to simulate a fluid flow on the aeroplane instead of moving the aeroplane in the computational domain? This both way you can do. This way you can do, or this way you can also do. But my target is to see only the fluid flow over the aircraft. Is it?
Yes, sir.
So my target is only to see the fluid flow over the aircraft. I will now fix my aircraft here, and I will allow the flow to see, and I allow the flow over the aeroplane, and I will focus my frame, my concentration on the top of the aeroplane. How the flow is, how the flow velocity and pressure are changing on top of the aeroplane. Got it? Anyone has still query on this particular idea? Why we are not simulating in the first type of way? That means this is the first type of way. You fix your amount of area. That means some area in the real life space, and allow your aircraft to move from point A to B. And while it is moving from point A to B, you see the flow, how much of pressure is acting on the aeroplane, what are the forces generating on the aeroplane. This is one perspective, the 2D simulation. And another perspective is fix your aeroplane in this domain and allow the fluid to flow on top of the aeroplane. My requirement is to see only the fluid flow on top of the aeroplane. So I don't want to bother about where it is going. Maybe it is going from India to New York or India to wherever, Washington, whatever it is. Let it go to somewhere, anywhere. I don't want to bother. I want to see only how much of pressure distribution is acting on the aeroplane. So I can fix my frame to the aeroplane and allow my fluid to pass over it. Hope you all understood this. How many of you
Yes,
understood
sir.
this concept? Okay, fine. Five. Good. So I believe that you understood this concept. If not, please let me know your queries. Then we will go to the next slide. So what are the key things that we need to understand while learning, before learning this CFD? So there are few things that you need to be very careful about CFD. The first thing is the mathematics. The first thing is the mathematics. You need to understand the mathematics behind the fluids and the solver.
Sir,
Solver means yes. Who is this?
sir, I have a doubt, sir, that the
Yes,
blue
Samay.
color in that car is the speed of that speed at that point, velocity of that point is related to that other points, or it related to some reference point.
Related to inertial frame of reference. Suppose you are standing there, you are standing on the ground, not on the vehicle, you are standing on the ground. Okay, with respect to
Okay, sir.
you, who is standing on the ground, with respect to you, that is the velocity that you are seeing. Got
Okay,
it?
sir. Okay, sir.
Because you are keeping your car as stationary and allowing the fluid at that velocity, and you are standing on the ground. The car is stationary, you are also stationary, you are both are on the same frame of reference, and fluid is passing. And this velocity is corresponding to what is the velocity that you are feeling. Okay,
Okay, sir. Yes, sir.
so please down your hands, everyone. So to generate these kind of contours, or to understand this kind of contours, or to generate these kind of contours in any software, any commercial software or the open source software, you need to clear with the mathematics, and you need to be very confident in the fluid mechanics. Fundamental fluid mechanics is very much essential to understand the clear physics of a complex object. This is very, very complex object. You see, there are many components in the entire airplane. You see, there is a circular component here, there is a rectangular one, and here is a long spherical one, and here is a tail also. Let me say is horizontal tail. So everything, there are many components involved in this. But in fundamental fluid mechanics, you already learn few things like I can say a simple object, a sphere is there, a rectangle is there. I don't know whether it was taught to you or not. Fundamental fluid mechanics says always about simple objects. What happens if flow is passing over a single sphere or single circle or cylinder? So simple things. So you need to understand the analytical reasons of those fluid mechanics, or many complex equations involved in the fluid mechanics. And then also you need to understand what are the fundamentals of CFD. Then only you can kickstart with your CFD softwares. You go with very as a pro with CFD software. So you can handle many things in the software as you are very familiar with the mathematics, fluid mechanics, and fundamentals of CFD. So this class is only teaching you some fundamentals of CFD, assuming that you are already aware of some basic fluid mechanics, no need of very advanced. And also I hope you are mathematics. Okay. Yes. So let's go to the next slide. It's already too much time that we spend on the first slide because to give the introduction of this computational fluid dynamics. So the second thing is what actually the basics of computational fluid dynamics involve. The basics of computational fluid dynamics involve with the governing equation, starting with the governing equations of a fluid. So in the governing equations, I just want to get the answers from you in such a way that how many of you know about this Newton's second law? Very famous law. Please raise your hand if you're familiar with this Newton's second law. Just raise your hand. Okay. Okay, good. So, how many of you know about mass conservation? Mass conservation. Ajay, you don't know what is mass conservation? Anyone else? Sayak, do you know what is mass conservation? Can you give me an idea what you have in your mind? Like what is the mass conservation according to you, Sayak? Can you unmute yourself and have a small interaction? Sayak, are you there? Can you tell me what?
Yes, sir. Yes, sir. I'm here.
Yes, Sayak. What do you know about the mass conservation?
Um, so, the law of conservation of mass that state it states about the inertia when we move. Hello.
Yes, Sayak. Tell me.
Sir, it states about the inertia when we're moving something or move somewhere.
Not correct. Anyone else who is interested to at least conservation of energy? Energy, who can tell conservation of energy? Iqbal sir will get angry like if you are not able to tell the conservation of energy. Iqbal sir, am I right?
No, it's okay. They will tell.
They will tell. I hope your students can tell the answer for this. They are brilliant at this.
Sir, shall I Can I tell the answer, sir?
No, no, you are not Aniket. Anyone else? Pranjal, Pranjal Bhattacharya.
Mass flow
Can
rate means
I tell?
the mass is conserved across the cross section where the fluid is flow.
Mass is conserved across the fluid flow. What do you mean by mass is conserved?
Which means that if in a pipe there is two different cross section area A1 and
Okay,
A2, and the fluid is flow from it. The mass
okay,
entering the area 1 is equal to entering the exit the area 2 is same. The difference in velocity is can conserve the
mass
masses.
and
A1 is equal to A2.
okay, very good. That's correct way. But one more single line statement I'm expecting. How many of you know energy conservation? I hope everyone knows about the energy conservation. Okay, please tell me the statement that you know about the conservation of energy. Mohit, can you tell? Mohit, Kayak?
Sir, can I?
Yes, Nijam, please.
Sir, energy and never be created or nor be destroyed. This is also a statement of the energy conservation.
E- Exactly. Very good. Very good, Nijam. So in the same way, can you frame the mass conservation? Replace energy with mass and tell me the statement. Yes, Mohit.
Sir, mass is never be created or
Never be.
never be created, never be.
Okay, fine. So I hope everyone got the idea of that. You cannot destroy the mass and energy. Got it? Yes, Ajoy. You want to tell something?
Sir, actually, mass conservation is in a chemical reaction, mass is neither created or destroyed.
Hmm. Never created, never destroyed. Yes, yes, Aman. Nice. Thank you for your answer. So very good. So I hope everyone is now clear. What are the fundamental laws that we should ensure while before starting with this CFD? The CFD is completely relied on the three laws: the conservation of mass, that you cannot destroy the mass or you cannot generate the mass. It's always conserved. If at time instant t, if there is certain amount of mass and after t plus delta t time instant for 1 second, if it is 10 kg of mass, and after that also, if you are not adding or removing the mass, uh, after some other time, the mass is also conserved, the same 10 kg of mass, whatever the system it undergoes. Okay. And the second thing is conservation of energy. You are very well known what is this conservation of energy. I need to introduce that energy is always conserved. Okay. It may transform from one form to another form based upon the process that you are following. And the third one is conservation of momentum. Conservation of momentum. How many of you know about this conservation of momentum? Mohit, you know what is the momentum conservation?
No, sir.
Okay. The same way how we are conserving the mass and energy, momentum conservation is also nothing but the two parameters. Momentum is nothing but mass times the velocity of the object. So one good example is that momentum conservation for you better, for very good understanding. Let me take some time to help you to understand the momentum conservation. So I have four pendulums here. Okay. So now I have four pendulums here. I'm just moved one pendulum this much distance and all three remaining pendulums are very close to each other. Everyone aware of the pendulums, right? Simple pendulum. I hope everyone is aware of the simple pendulum. I just moved only one ball, one pendulum like this, and I allowed it to move at high speed and hitting this last pendulum, this one. So can you tell me which pendulum, like whether the single last pendulum will move, or the last two pendulum will move, or all three pendulums will move forward by hitting up by due to the hit of this single pendulum? Just tell me your answer one by one. Like how many of you say that only last one pendulum will move due to the hit of this single pendulum? So four people, 5, 6, 7, 5. Only 5 people are saying that. 6. Okay, fine. Let me fix this. So 6 people are saying that because of the single one pendulum, I am uh, allowing to hit all these three remaining pendulum. Only this single last pendulum will move to the right. Okay. Now, how many people are saying two pendulums will move because of the hit of this single pendulum? How many of you saying? Please raise your hand. Because of this, I'm pulling this one pendulum forward, backward, and allowing it to hit these three remaining pendulums. Now I'm saying that two pendulums here, this one and this one, will oscillate to the other side. How many of you saying two will oscillate? Parvar, you are saying two oscillates or one oscillate? Nijam, are you saying two or one?
One, sir, one.
Nijam is saying only one is oscillating. So how anyone saying that two
One,
will
sir.
oscillate? Okay, anyone saying that two are oscillating? Can you please raise hand? And remaining, please raise down your hand. So Ajoy is saying two will move to the right. Ajoy,
Yes, sir.
so you're saying two pendulums will move to the right, is it?
Yes, sir. Yes, sir. Actually.
Two pendulum, okay. How many of you saying three pendulums also? All these three pendulums will move because of the hit of this single pendulum. Nijam, please down your hand if you are not.
One, sir.
Only one, okay, please down your hand. So most of you said only one pendulum moves to the right. Okay, so the correct answer is if you are hitting with only one pendulum at the left, only one pendulum at the right will move with the same velocity, with the velocity that hit you at the left. Because all these pendulums are with the same mass, all these four pendulums having the same mass. If you pull one pendulum out of this combination and allowing it to hit with some velocity, then the same velocity and the same mass, the last single pendulum only will move. These two pendulums will remain static. They don't move. They just transfer the momentum consist with this pendulum to this and this, and only this will move to the other side because all momentum is transferred to this only one pendulum, this last pendulum. Got it? So in the same way, now I will ask one more question. If I am pulling out two pendulums like this, and two pendulums are like the statically. Now I am allowing these two pendulums at a time to hit these two pendulums. Now tell me how many pendulums will move to the right? Only one.
Sir, two pendulum.
Okay, two pendulum. How many of you are saying that both the two pendulums moves to the right?
Two pendulums.
Okay, 4, 5, 6. Okay, 6 people are saying that both the pendulums moves to the right. Very good. So because of the momentum conservation, what will happen? As the mass of all these pendulums are same, since you are giving the momentum equals to two pendulums, so both the other two pendulums will move to the right. Okay. So the third final one is this way. I'm taking out three pendulums to the left and allowing them to hit to the single pendulum. Now, can you tell me what will happen? Who can tell this answer? I took out three pendulums from the first collection. This is of my first collection. I took out. Mohit, can you please down your hand? Mohit?
Sir,
Yeah. Put down your hand, like, or you want to tell something. Okay, fine. So now I am pulling out three pendulums out of the system like this and allowing them to hit to this pendulum, the one you are seeing here, the only single pendulum. So what will happen now? Who can tell the answer?
Sir, 3.
Who? Sayek?
No, sir,
Who
I am
is that?
Ajay.
Hi, Ajay. So what will happen? Three pendulums will move.
Yes, sir.
So what are the three pendulums? I will just give a number here. This is 1, 2, 3. What are the three pendulums will move?
Sir, last 3 pendulum, 2, 3 or 4.
2, 3, and 4. Why not? I can say not 2, 3, 4. Why not 4 will move? So
Sir,
here you
2,
need to understand. Yes, yes. Come on.
sir, 2, 3, 4 also move, sir.
2, 3, 4 also moves. That's fine. But
Yes.
what will happen to 1? 1 will remain as a static, or it will also move. Okay. You need to understand the conservation here. Here, my mass is same for all the pendulums, and I'm giving the momentum equal to 3 times mass m1. If I say m1 is the mass of each pendulum, every pendulum, I'm saying m1 is each pendulum, and I'm giving some velocity v. So this is my total momentum. So if this momentum is transferred into this ball, the amount of momentum should be conserved in such a way that either the velocity of this ball should be increased, or the momentum, that product, 3 times m1, this should be constant. Okay. This particular parameter, that is mass into the velocity, that is what we are saying generally as the momentum. So this momentum should be constant. So to ensure this momentum is constant, so the pendulum, this fourth one, third one, and second one, moves together, leaving this first one as a static. Again, if they are going to the right and will come back again left because of this pendulum action, the three will move to the right and will come back again and will hit the static single one. So again, the momentum should be conserved in such a way. I hope now you get some idea how this momentum conservation is happening. Everyone is clear about this momentum conservation? If not, you can raise your hand. I can try to help you to understand better. Everyone understood this? You have doubt? Yes, Sayak? Okay. I hope you all understood this. If not, if you have any doubts, please you raise your hand. Priyanshu? Okay. I hope you all clear with the momentum. Yes. Who is that? So you all clear with this momentum conservation. So all these three laws you should keep in your mind. The three laws are first is mass conservation, and second is momentum conservation, and third is energy conservation. So keeping these three laws in your mind, you should forward with the computation fluid dynamics. These three laws are playing key role, or these are the base for doing any kind of simulation. The simulation that you are doing should obey or should follow these laws. Everywhere in your simulation, you should follow these laws. So most of you know the right side equations based upon these three laws. One is the mass conservation, and second one is the momentum conservation, energy conservation. This first one is the mass conservation, very simplified form. There are much more lengthier equation is there. We say del dot v bar equals to 0. How many of you know, or how many of you are aware of this del operator, del dot? This v bar is velocity. How many of you very well aware of this del operator, del dot? Only three? Del. Uh, Most of you know from your mathematics, I guess. Okay, fine. So if you are not aware, then it's also fine. Then so, and the second thing is the momentum conservation based upon the. I suggest if you are interested, you can look into the derivations of these equations. How these equations of continuity means continuity is mass conservation. I'm telling you again. This continuity means mass conservation, how this mass conservation equation was derived, and how the momentum conservation equation is also derived. You can go back to fluid mechanics and you can try to learn by yourself. And also energy conservation equation is also there that I am not going to discuss here. So from these complex partial differential equations, we got a simplified equation of A1 V1 equals to A2 V2. Someone was telling that, I guess Sayek or Nijam was telling that mass conservation is if you're taking one cross section A1 and another cross section A2, so the amount of mass at A1 and A2 is same. Who told that answer about the mass conservation?
Aman sir.
Aman, are you there? Okay, Aman told this answer. So this is the correct answer, but the derivation started from the conservation of mass and ended up this simplified form of equation. And further simplified form of equation is mass conservation is A1 V1 equals to A2 V2. Okay, so here also there are many assumptions that you need to understand how we got into final this particular equation. Okay, and the second thing is the Bernoulli equation. Anyone can find out where is the Bernoulli's equation in this complete figure, I mean complete set of equation. Where is the Bernoulli equation? Anyone can find out? Yes, can you please tell anyone? Anyone can unmute yourself and can you tell where is the Bernoulli equation in this set?
Which equation, sir?
Aman,
Yes, sir. Which equation I have to mention?
where is the Bernoulli equation in this set of equations? Can you figure out the Bernoulli equation in this? So the Bernoulli equation is hidden here. So this one is the Bernoulli equation. Okay, this comes after simplifying this big equation. You will end up with this small form of Bernoulli equation after simplifying this complete partial differential equation. Then there are also so many assumptions are there to simplify to this small format. Okay, so you can see there are many equations from your fundamental fluid mechanics or fluid dynamics, whatever. So from those equations, whatever you're all seeing here, they are originated purely from this mass conservation equation, momentum conservation equation, and your energy conservation equation. So these three you should be very aware of that to understand the complete compression fluid dynamics. Whatever the simulation you are doing in compression fluid dynamics, those simulations should obey these laws. Okay. Fine. Let's go to the next slide. So what are the simple steps in? I request everyone to please take a note of from this particular session, from this particular slide. It is very important for all your upcoming lectures. So I will be using this terminology for all your remaining classes. So computational fluid dynamics is involving in the first, so mainly divided into three sections. One is pre-processing, okay, and solver execution and post-processing. So what are the subsections involved in these three things? If we just look into that, then you will clearly understand what is this pre-processing, solver execution, and post-processing. First one is modeling a computational domain. Modeling a computational domain means you should understand what is the amount of frame that I am creating. Suppose if I want to simulate a flow over an aeroplane, I can do in two methods. I told you both the methods, the method 1 and method 2. That is, you can move the aeroplane in the amount of frame. If this is the amount of space that you captured in the real life, and you are simulating in your computer, this is the amount of space. And here you have an aeroplane. And here you have an aircraft here. So if you are simulating in such a way that the aeroplane is moving from left position A to position B, you can also simulate here, or else you can fix your aeroplane like this in this space and allow the fluid to move over the path of it. This is method 2, this is method 1. If you're doing in this method 1, your aeroplane is moving from A to B and will end up here because your fluid is static. But my target is to see only the fluid flow over the aeroplane. I don't want to see anything else. So I fix my frame and I allow my fluid to pass over the aeroplane. Both are same in the relative sense. So if both are same, I only look at my second concept. In the second concept, what I need to do, in both the ways, you need to set up one frame. Some particular area you need to fix up to see your simulation. Because if you want to see only the flow over an aeroplane, you cannot only take this small area. You cannot only take a small area, or only the aeroplane is not sufficient to do this. You need to take up the space, three-dimensional space or two-dimensional space. So I'm taking a two-dimensional space like this and placing my aeroplane here. Then only I can see the entire flow field in this two-dimensional space. So two or three dimensional, whatever the dimension is. So you should fix your space here like this. So for this fixing of space, I need to model a computational domain. This space we say as a computational domain. Okay. So now I fix some space. That means you are seeing an aeroplane. You should understand that you are seeing an aeroplane means with your eyes. You are not only seeing the aeroplane, you are also seeing the space around the aeroplane, right? So that also you need to model in the simulation. So this is the space around the aeroplane, and the aeroplane is here, and you are focusing only on the aeroplane. So you will feel like the fluid is flowing on top of the aeroplane, but not the aeroplane is moving. So aeroplane is static in this space and fluid is moving on top of it. So this space we say as a computational domain. So now you just understood what is a computational domain. And then inside that you need to create your geometry. The geometry is aeroplane. This is my geometry and this is my computational domain. Okay. Okay. Mohit Sharma, you have any question? I am seeing that you raise your hand for something.
No, sir.
Yeah, please down your hand. I see your hand. Okay. So next thing is mesh generation. In this CFD, you need to be you need to get some skills in the mesh generation. What is this mesh generation means? You are solving the equations that comes up with the mass conservation or energy conservation or momentum conservation. Those equations will be solved by creating the mesh in the domain. Mesh means you need to make your complete computational domain into small parts. All completely. You need to make your complete computational domain into small parts. So at every small box, I'm telling in a complete layman version so that you can understand it better. So in that every small box, you are going to solve your partial differential equations. So those partial differential equations will be solved at every small domain, and you will get the information of velocity and pressure in this every small box, either at the center of the node or at the edges of this cells. Okay. So this information, whatever the information of velocity pressure you are getting, you are going to store this information at these boxes, either at the center of the box or at the corners of the box. Hope you all understood this, right? This point should be very clear. Where you are storing this information. I told you that you are getting the pressure and velocity. So where you are storing this pressure, velocity or temperature also you can get. So where you are storing these things, you should store at the every box. You should make your computational domain to small box and store the information of pressure and velocity at the center of the box. Okay, that is about the mesh generation. And you need to understand what are the governing of equations. Governing equations corresponding to governing equations means the partial. Yes, sir.
Sir, actually, I have a general question regarding this computational domain. Like for external flows, we can design the computational domain like whatever you are showing for an aircraft. If we are we are designing the computational domain, we can like design it likewise. But what about the internal flows? If we are analyzing an internal flow of, for example, turbopropeller engine, where we are analyzing the internal flows inside the engine. So how to create the computational domain in that case? Like for the internal flows, how we will decide the computational domain?
there you're also closed with your computational domain in such a way that suppose if I say a simple convergent divergent nozzle, how many of you know about this Venturi meter? Venturi meter you have performed right in your basic mechanics, not basic mechanics, in your fluid mechanics lab. So Venturi meter is saying that the fluid is allow coming from here and it gets accelerated and it will again decelerated. So some use of some flow meter measurement, the amount of volume flow rate measurement that you use your Venturi meter. So here you don't need to model any three-dimensional space or extra space out of this around the nozzle because your fluid is restricted inside this geometry. So you only need to model these walls, only the convergent divergent nozzle or the convergent divergent duct. But in external aerodynamics, your fluid is not restricted only inside the geometry. In the internal flows, your fluid is restricted to between these walls. Whatever the walls you are seeing, this is the wall and this is the wall. So your fluid is restricted between these walls. So you don't need to model any big computational domain. This will be your computational domain. But in the external flows, your fluid is not restricted. Your fluid is allowed to pass over the object. So you need to fix your fluid or fix your space, some space around the object. Arhit, do you get the answer for your question?
Yes, sir. Yes, sir.
Okay. So I am telling mainly focusing on the external flows as we're discussing about in this session or complete the tutorials, mainly focusing on the aerodynamics. Okay. And then you need to give the boundary conditions. The partial, I told you that the governing equations involves with the partial differential equations of different types. How many of you aware of the partial differential equations or differential equations and solving those with initial conditions? I hope you are all very well trained in that, solving the partial differential equations or differential equations with the initial conditions. Gutta method or Simpson's rules or many integration methods. Very good. So these governing equations also involve with the partial differential equations, and you need to set the boundary conditions like what is these boundary conditions nothing but suppose this is your computational domain, right? And this is your boundary. This is this first boundary. This is the first boundary. And at this boundary, what you need to give the condition is at this boundary, my flow is having a velocity of v equals to suppose 50 miles per hour. Okay, so this is one boundary condition. And also at the same time, another boundary condition is pressure P is equals to some atmosphere, 1 atmosphere pressure. So this is another boundary condition. And you can also specify boundary conditions in higher derivatives. I don't want to confuse you. So this is one boundary. So I need to specify these values for progressing the or for calculating the velocity and pressure and the remaining small domains. In the same way, here also you need to specify your velocity and your pressure. Also, you need to specify what about the velocity on the top here. This is also one boundary, right? So you need to specify here what the velocity. Here also you need to specify the velocity and your and this is also a boundary because boundary is nothing but your interacting with your fluid here because the fluid cannot pass into the aeroplane, right? If the fluid is able to pass into the aeroplane, then you need to specify. Here you need to specify that the fluid should not pass into the aeroplane. That is also one boundary condition. How many of you understand this question? You should set some boundary condition saying that the fluid should not pass into the aeroplane. That is also one boundary condition. How do you set that kind of boundary condition that we will see later on? But did you get this question or not? That I'm saying that you should apply some boundary condition such that the fluid should not pass into the aeroplane. The fluid should pass over the aeroplane only. Got it? Everyone understood this boundary condition? This is very important because the fluid should not pass into the, into the aeroplane, right? The fluid should not go into the aeroplane. It should pass over the aeroplane, right? So that is also a condition. We say the boundary condition. How many of you clear with this boundary condition? Just raise your hand. Fine. Nice. So those boundary conditions also you need to specify. After specifying your boundary conditions, you need to run your simulation. Simulations running means you need to solve your partial differential equations to get the velocity details or pressure details in your complete computational domain. Once you get velocity and pressure details, you will gather the results. Whatever the simulations that you perform, you will just gather those results and then you will analyze for your requirement. What are the requirements? I told you at the beginning, my requirement is to see the how much of forces are acting and what are the causes of those forces. So for the causes of those forces, what I will analyze the pressure distribution on the aeroplane, velocity distribution on the aeroplane. So these things I analyze from my simulation results. So these are the key steps in your computational fluid dynamics. So you take a note of all these key steps, then we can proceed with the simulation. So I will quickly go through the remaining slides as I described you that I will also show some.
Sir, I have a question. Like,
Yes, sir.
sir, for example, we are simulating any 3D flow, like a flow over an airfoil or a flow over a Formula One car. So the model is it is having some values in the z-axis also because it is 3D. So the thing is, sir, while we are, sir, can you just show your last slide? Sir, like you have discretized this like in a 2D form. Sir, for
Yes.
that case, in case of a 3D modeling, or if we are analyzing any 3D or solving any 3D flow, sir, sir, are we going into the finite volume method, or what is the difference between finite volume method or finite element analysis? Like, so 2D element, are we taking, or are we taking a volume in that case? So,
Finite element method, finite volume method is a way of approach that you are solving your partial differential equations. It is, you can take a finite element method also, finite volume method also. It is just a method saying how to solve your partial differential equations that you are handling for this particular problem. Like, are you aware of this partial differential? I hope you are aware of the partial differential equations. You can solve your partial differential equations by using a Rangai-Kutta method, right?
yes, sir.
Rangai-Kutta
Yes.
RK method, or also you can use any other numerical techniques, integration methods. I can say trapezoidal rules, or also you can use Simpson's one-third rule, and many other methods you can use for solving those partial differential equations. In the same way, those are straightforward for your particular simple form of uh, governing equations. If you have a complex partial differential equations, okay, are you getting?
Yes, sir.
If you're having a complex partial differential equations, you cannot solve those things analytically for all the flow field. Like you need to use the numerical techniques. The numerical techniques is the first. There are many things are there. That is a finite difference method, finite volume method, finite element method, and the spectral method, and so on. There are many numerical methods. But why you are specifically focusing on finite element method and finite volume method? Like, do you know anything about how we are using the finite volume method, finite element method?
No, sir. I haven't like studied it
Okay,
yet.
maybe you, yes, someone. Okay, maybe you are heard about the finite element method, finite volume method. Finite volume method helps you to in fluids, simulating the fluids, and people generally use finite volume element method for simulating the structural things, and finite volume method for simulating the fluid flows. But it is not necessary to use the same finite volume method with fluids. You can also use finite element method. It is an integration method of solving the method for partial differential equation. You can use both also for different purposes. But you need to find out the suitability. Which one is suitable for this purpose? Understand?
Yes, sir.
Because of the conservativeness property of the finite volume method, the finite volume method is more suitable solving the fluid flow problems, I can say.
Okay, sir.
Okay. So these are some applications of CFD. The key applications are this is a Tacoma bridge that, like I say, many of you see in the videos. A bridge was shaking like this, and it got fallen. I mean, it got collapsed. Not fallen, it got collapsed. because of the heavy wind. So that physics involves that kind of collapse is like involvement of more vortex shading or aeroelasticity kind of features. So there the fluid is playing a very key role. The velocity of the fluid and the structure of the fluid that is flowing on top of the bridge. I will do a video here. So we'll try to show the video the next time. So you might have seen in many videos that the bridge was shaking left and right and abnormally and got collapsed. That incident is because of not proper taking care of the aerodynamics. If the engineer has taken care of the proper aerodynamics and the involvement of aeroelasticity concepts by doing a computational fluid dynamics or any other techniques, then you will understand that there is something like this kind of phenomena is happening. So that we need to tackle it before constructing this kind of bridges. So how do you know that this kind of thing, some kind of collapsing kind of phenomena is happening? You should do a CFD analysis, a computational fluid dynamic analysis. Then only you will come to know that there is some kind of destroying phenomena is happening when the fluid is passing at this particular velocity. So you should take the measures and you should not design in such a way that it got collapsed by the fluid flow phenomena. In the same way, the tsunamis also happens because when there is a big movements between the Earth's plates, like continental plates that you can see that when there is a movement between those plates, you will see a big waves, a very strong waves, that may cause casualty to a tsunamis also. And also in the rocket analysis, like space entry vehicles or the re-entry vehicles, which travels at very high speed. Okay, and very good applications are simulating the fluid flow inside the blood vessels, nerves, many things inside your body. People are trying to simulate the fluid flow inside and how the fluid, not only the blood and also the air, how the air is passing into our body and where it is going, and how to simulate the heart and passing of the blood into the several nerves of our entire human body system, and how the clotting is happening. So these kind of things also you can simulate in the by using help of the CFD. Okay. So there are many other things. Why only CFD? Why can't we do experimental analytical also? Analytical also some restrictions that you cannot do all the things in analytical. Very simple things that you can study with the analytical answers. Experimental, it is not all the time feasible to study with the experimental. Okay, you have only certain possible things you need to scale up, or you don't need to do a wide range of experiments because it involves most costlier. So the simulation is much better because you can do multiple things with less cost. Because compared to the experimental, the simulations are less costly. You are modeling everything here with maths and mathematics, and you are doing the simulations with some computer. So CFD involves understanding of type of flow. Before simulating your flow over an object, you need to understand what type of flow it is. There are several types of flows that whether you are the first thing that we do, we and I discussed it, I raised the question that how to simulate that internal kind of flows. So first you need to discretize your object. You need to have a problem, some problem like saying whether it is an internal flow, whether this fluid is passing in through an object, or you need to define your problem whether the fluid is passing over the object. So these things, and at the same time whether fluid has a compressibility. Fluid can be compressed or not. A fluid has incompressibility or heat transfer is there, whether it is involves non-linear in time, or what are the conditions of viscosity, what is the laminar, whether it is a laminar flow, turbulent flow. Many things that you need to have a pre-idea before starting your simulation. Okay, I don't want to involve these many things, but experimentally you can see if you have any idea from the simple set of experiments that you see in the real life. There are the flow structure. Based upon the flow structure, people used to call this as a laminar flow, this as a turbulent flow, or this as a supersonic flow. Okay, and this involves the shocks. So those kind of things that people used to. This is already well framed in the in the books or the literature of the aerodynamics. So at the beginning, I clearly gave you short introduction of what is mass conservation, what is momentum conservation, energy conservation. So here you can see the complete set of the partial differential equation. So the momentum conservation involves three x and y z momentum equation. All these equations should be solved in your computational domain. After solving these equations only, you will get the information of the pressure, velocity, and temperature in your computational domain or over the aerofoil.
Okay, so solving these equations, you need a finite volume method or any integration method. Those methods are incorporated in the commercial softwares like ANSYS Fluent or any other Inkscape or OpenFOAM. So those methods you can use and you can solve these equations, and these equations will give you the flow field around your object. Whatever the object that you're simulating, that comes, the flow field comes by solving these equations only. And also you need to understand how these equations are categorized. Okay, what is the many of you know well about whether the equation is parabolic equation, the partial differential equation is parabolic or elliptical or hyperbolic. I can better explain this elliptical, parabolic, hyperbolic when I can get a chance to explain what are the different types of flows, because there are some kind of supersonic flows, subsonic flows, laminar flows, turbulent flows. There are many flows. So each flow is governed by some particular type of parabolic equation, and the information is also, I mean, the type of equation itself is saying the type of what type of flow that you will be getting. Okay, so I don't want to take that because it is completely complicated. It makes your mind complicated. So okay, if you are interested, you can just have a look at this reference. I can share these slides with you all later on. You can find out what are the partial differential equations and how to use those partial differential equations in our real life fluid flow problems. How to discretizing those partial differential equations. So now comes to our final slide. This is where I started beginning that I told you that please take a note of all these things. So as I said at the first, you need to create a mesh around your aerofoil object. So I'm taking some shape. I don't want to say what kind of particular confuse you by saying the name or details of this shape. So I'm taking some shape. It is looking like more or less some ellipse, more or less ellipse. I don't say it is a perfect ellipse. So some shape I'm trying to simulate. So this is my ellipse. So on this ellipse, I want to simulate the flow over this ellipse. Okay. In the aerodynamics terminology, we mention this as an aerofoil. Okay. On this aerofoil, we are simulating the flow over. I want to simulate the flow over this aerofoil. So what I need to do, I need to create the computational domain. My aerofoil is here. You can see this is my aerofoil, very small aerofoil here. So around this, I created this big computational domain. So my frame is seeing not only this aerofoil and this entire space. This is my complete space. I'm seeing the complete space and my aerofoil is here. So now this is my computational domain and this is my aerofoil. And the third thing what I need to do is I need to discretize into small cells. You can see I discretize everything and then the computational domain into small cells. Okay. Now at this every small cell, my equations, my partial differential equations will be solved by using the finite volume method. So finite volume method will solve my partial differential equations and gives the information of velocity and pressure based upon the boundary condition. What is the boundary conditions? I need to set inlet velocity. You see the arrows here. These arrows are saying that there is some finite inlet velocity. Fluid is passing through this inlet with some velocity and exiting here, entering here like this, and exit is here. So coming inside here and exit here. So these boundary conditions I need to specify. Some fluid is entering into the domain with some velocity and leaving with some particular velocity. Based upon this boundary condition information, my solver will solve the information of pressure and velocity inside the domain and around the aerofoil and gives the information of velocity, pressure, and temperature. I use those information to understand what are the causes of forces of generation of forces or change of temperature, any parameter on this particular object. Okay, so I hope up to this is clear for everyone. Let me know if you have any questions. That is, if you don't have any questions, I will quickly move to the. I will quickly show some simple example of computational domain and ANSYS Fluent. Do you have any questions? Any questions so far? Okay, how many of you understood the steps so far I explained here? These steps, only especially these steps. Don't need to be all the steps, especially the computational domain, the geometry creation, the mesh generation, and the governing equation or the boundary conditions. How many of you understood these things? Please raise your hand if you understood these. So I believe that you understood up to these parts. For you can get better understanding while you're handling with the software that we will see from the tomorrow onwards. So the next steps in your this short-term course, today I explained you what is the applications and introduction to the CFD, and I will show you some small example, not a big one. And then tomorrow we will discuss the user interface tool with the ANSYS workbench, and you can go through all these contents that I shared with you all. And finally, we will end up with the simulation of an airfoil in the ANSYS print. This is our final target. Okay, so let me dive into the. Let me take one or two quick questions, then I will show you the ANSYS plane software, the ANSYS software basically. Any one or two quick questions? Okay, if there are no questions, I will move to the ANSYS workbench. So how many of you installed the ANSYS in your own laptops or have seen the ANSYS previously? This is a commercial CFD software. How many of you installed in your system or laptop? We have also you have if you have seen it previously, not seen it, just a user interface or you know about it. You already know, or just heard. At least if you have the ANSYS, there is some software like ANSYS to simulate the build. Just raise your hand. Okay, good. So now the installation of ANSYS in your, if you have a laptop, you can install in your laptop. This is a free student version ANSYS student software. Also, we discussed that you will get ANSYS student software in your laboratory also, where you can work with your software. And here, after installing, you can open your software by using the workbench. If you type from your start, you will get something like workbench. You should not type like ANSYS. You should type like a workbench. Workbench is some kind of setup environment where you will get the products of ANSYS, all the products of ANSYS. ANSYS is involved in this. Everything is involved in this workbench. Okay. If you open this workbench, you will get the interface of this workbench. Okay. I don't want to go to the details of all the tools available in the workbench. I hope my screen is all right for you to see. So there are many tools available in this workbench. We are only focusing on this particular tool that is called Fluent. How to get this Fluent software and what is this geometry, mesh, everything. Everything we will see in the subsequent sections. But what you will finally end up with. Let me show you the mesh I generated, and we can have a discussion. We can have a discussion on that. Okay. Aman, are you there? Aman? Aman, can you hear me? Uh, Anyone who wants to be a volunteer? I just for a small interaction. Mohit?
Yes, sir.
Yes, Mohit. Mohit, I hope you followed the lecture so far. If that is the case, can you tell me what you understood from the image that you are seeing on the screen? Mohit, I'm hearing a lot of noise from your end. Anyone can tell me what do you understand from the image that you are seeing on the screen from so far from the discussion I taught you. Yes, sir.
Sir, the computational domain, and it's a cylinder that we are analyzing here. It is the
Yes,
computational domain, and it is discretized using this some structured mesh.
using some structured mesh. Okay, you know these things well. I need to explain you. Who else? Who else can answer this? What you understood from this that I want to know from you. Aman, are you there? or whoever interested, they can just raise their hand and otherwise I will ask. Yes,
Yes, sir.
Anand.
Yes, sir. Yes, sir.
Yes.
Sir,
So
here
what
is a share is analysis. UMS
here is a
analysis of
square
a square.
analysis of a
Uh,
square or analysis of a circle?
Analysis of a circle, sir.
Analysis of a circle. So everyone please point it out that it is an analysis of a circle, not analysis of a square. My square is the space I captured. I am seeing through some camera and I am seeing a circle, but I don't see only the circle, I see also the space around the circle. So that space I took as a square. Okay, I took a square space and a circle is in between that. Okay, Aman. Next, what do you understand? Let me ask Pragya, Pragya Sarkar. Pragya Sarkar, are you there? Priyanshu, Priyanshu, just let's have a small general interactive talk, not in detail. I don't want to, I'm not asking any deep questions. If you know, you can just tell what you understand. If you don't know, you can just say, sir, I'm not aware of this. I did not follow. Like, you can just say like that. I have no issues. Priyanshu, please unmute yourself and we shall have a small interaction session. Sayak, are you there?
Yes, sir.
Yes, Sayak. Sayak, what do you understand from this so far from my lecture and seeing this image?
Sir, that is a circle which we will discuss about, and the square is the domain which we discuss.
Okay. My question is now, are we simulating the flow that is passing through the circle or passing above the circle or flowing around the circle? Which one we are simulating?
Sir, around the circle.
Around the circle. Very good. So, what is these small boxes that you are seeing? What are the small boxes that you are seeing? Is that any name that you heard from my lecture so far?
Sir,
What is it?
I forgot the name, but the that was the boxes which were sorry, where we will analysis the um analysis the velocity,
Yes.
pressure, and etc.
Yes. So, in those boxes, you will get the information of velocity, pressure, and temperature, all the primitive variables of the fluid flow. Got it? Very good. So
Yes.
this is the mesh software, meshing software. That means you will get the geometry, and from that geometry, you can create this kind of mesh. My aim is to simulate the flow over a circle. This is my circle, and my simulating the flow over this circle, how the flow is passing on top and bottom of the circle. So I cannot take only the circle to simulate this flow. So what I'm taking, I am taking a space around the circle, square space, and discretizing the domain. The domain means the area between the circle and the square. That is my domain. And I'm discretizing the space, the complete space, into a small boxes that we call as mesh. Okay. So that mesh we are discretizing. So I hope everyone is clear up to
Okay.
this part. Okay. Next, you need to simulate this. Just 5 more minutes. You will see the simulation of a flow over a cylinder with some values of pressure and velocity on top of the cylinder. How it looks like. I'll just show with some small example. I will give the complete details. So this software is designed in such a way that once you know basic steps, you can get the details of at least some approximate details of the flow physics, but not complete accurate details. If you want to get the accurate details, you should understand each and every step that you are doing in the solver. Okay, so each and every step understanding this, you should come up with the basics of all this mathematics to fluid mechanics and everything. But right now we are discussing in such a way that we are at least getting an approximate idea of how the flow looks like on top of this. So now, as I said, I need to give some conditions. So here, I don't have an option to give any kind of conditions here. So let us stop it here because I did not give, I missed some intermediate steps here that to simulate the flow over a cylinder, because what I need to do here is, this is my inlet, this area. I hope you are all seeing. So this area is my inlet. So at this area, I need to specify to the software that allow the fluid to pass with the velocity of suppose 10 meters per second. So it will allow the fluid to pass with the 10 meters per second. And I need to tell the software to whatever the fluid is entering from here, make that fluid to exit from this surface. Okay, from this surface, the fluid will get out of the computational domain. And I also need to tell my software this is my surface or this is my body, so that you don't allow the fluid to pass through this body. Okay, all these conditions I need to set to my uh, to my software. I need to give to my software. Then only it can understood that I need to allow the fluid at this velocity, and need to share that that fluid should come out from this domain from this boundary, and my fluid then the fluid should not go through this circular domain. Accepting these conditions, it will calculate the pressure and velocity in the every small boxes and will give you the final information. Okay, I hope you are all clear up to this. If I have some time, 7:54, I need to give some more conditions here. Then only I can say that if you should go like this and you should behave like this, whatever the structure I just shared with you, then only the software can understand these kind of conditions. Okay, so that's all for today. So if you have any questions, we have 6 more minutes. You can discuss the meantime. Any questions?
No, sir. Sir, I just have a general question, like related
Yes, sir.
to the computational domain as well as the memory space that we are using. Like, sir, while discretizing the whole computational domain, sir, is it taking some spaces in our RAM or our computer, sir? How will we minimize the space to simulate, like, to get a better result? Is there any relation between the RAM
That com
spaces?
that completely depends on your simulation type or what type of simulation you are doing.
Okay,
Then
sir.
what is the number? What is the number of cells, completely fluid cells in your domain? Okay, and
Okay, sir.
many things involved in that, because everyone is a beginner level. I will teach you that personally.
Okay, sir.
Based upon you need to see your hardware requirements and software requirements both. Then only you can perform the simulations. Otherwise, it is difficult. Okay,
Okay, sir.
we can discuss that one to one. Any more questions? So if you have no more questions, then we can call it a day. Iqbal sir, do you have any questions or you want to talk anything regarding this?
No, it's fine. Okay. For today, it was introductory. The session was good. The students are getting the brush ups their concept like conservation of mass, conservation of energy, and introduction to this answers. Okay, in the next or further talk will enhance. It was fine. From the
Okay, sir.
student, if you have any question, you can ask to sir. Any sort of question, basic
Any
question,
question,
any
what
question
we
you
are
can
going
you
to
can
do,
ask.
what we are going to do in the next few sessions, and why it is useful for me, what kind of applications, further more details of the applications, or are there any sort of jobs in this kind of area, or how it is useful in the research field if you are going for the higher studies later on. We can discuss that in the few minutes of time. Anyone would like to discuss that?
If anyone is having any sort of question related to this topic, you can ask any sort of question. Don't hesitate. You ask, you will get some idea. It's okay, sir. I think after 5, they all are exhausted. In the next session, we will have some question, more interaction.
Okay, can
Hope
I have
they
introduction? Yes, we can call it today. Can I have introduction to any of your good students here so that I can follow up them from the next class? I hope everyone is a good student, but who are want to interact here from the next session? That they want to follow for all the next sessions. At least they can show up a good interest in all the next sessions. Like I know Arihit very well. I mean to like he can do and he can progress it well in the coming classes. Any other students that I want to keep in mind that they can do it well like that?
here we have this Aman. We have Aman is
Yes, sir.
a good student over here. Then Chayok, Pranjal, they almost all are good. Mohit is also very active over here.
Okay, sir.
Mm, Nizam is also very good student, and these are the a good student actually. Okay, they all are good, but they are having some hesitation to interact. So
That should not be. Yes, sir. Yes.
Mhm. My request to all, don't hesitate. We are over here to learn. You all are over here to learn something. If you don't tell anything, you will not get anything. The fact is that to learn anything, you have to ask. More you ask, more you will learn. It's okay, sir. Overall, it was quite well. Uh,
Okay,
hope
sir.
hope we will have some more good interaction or more insight inside this topic. Okay, thank you, sir,
Okay. Thank you,
from my
sir.
end.
Thank
Sir,
you, everyone.
actually, I had some talk with Iqbal sir and also you regarding the tomorrow's timing. Sir, Iqbal sir, can you like discuss? Can we discuss, sir, regarding tomorrow's timing? Actually, uh, Manju sir is not here today. He's a teacher of fluid dynamics. He's busy in some event. But tomorrow also he will be going for that event. So he instructed me to take the class or conduct the class at 9:30 or in the first session or so, sir. Like, but there are few like issues in taking the class in the first half. So, sir, Iqbal sir, can we like conduct the classes in the first half? Like, since
No,
Manu sir could
no, it's okay. But you have to take the permission from HOD, sir. And in these days, we can't take the classes in the first session because it is the instruction from the authority. We can't take the session in the first half. So for that, you
okay,
have
sir.
to talk with the HOD, sir. If he agrees, then no issue. Okay.
Okay, sir. So.
Or better you can do its timing is okay, but let us see what will be the you please ask to the
Sir,
participant. Uh,
sir, actually, we have fixed the timing from 2:30 to 4:30. So I have asked permission from HOD sir also. He told that there is no issue from 2:30 to 4:30, but like tomorrow's class, since there is an event in which Manju sir will be busy again in the second half. So sir, he told me like if we can conduct the classes in the first half. So regarding only tomorrow's class, sir. Sir, will it
That is
be
fine. That is fine, but you have to talk with the HOD sir. You have to take the permission from HOD sir.
okay,
Okay,
sir?
without his consent, we cannot do anything.
Okay, sir. Okay,
Okay, it's
okay,
okay.
sir.
Okay.
If you can discuss with your HOD sir and you can get back
Yes,
to
sir.
us, no,
Yes.
fine. We can schedule whenever it is available, labs are available. we can do that. Okay, I
Okay,
hope
sir.
you all participants understood the things. I don't want to waste your time more than this. It is already running off the time. So, anyone having any questions, you can come back to me personally. Also, you can text me or you can email me. Okay. If you want my email, you can get it from Arhit. He will share in the group. Okay. Uh, it's already 8 o'clock. So, thank you all for joining. We'll see you tomorrow sometime. The schedule will be shared with you all.
Thank you, sir.
Thank you. Thank you, Iqbal sir.
Thank you,
Thank you,
sir.
Arhit. No, thank you all the
Thank you.
students for
Thank you.
joining.
It's okay. Fine.
Thank you, sir.